These dead trees are not a fire's aftermath. They are a warning from the last great earthquake. This is the Pacific Northwest, one of the most beautiful coastlines on Earth. But beneath this calm surface, something immense is building. Two massive tectonic plates meet just off this coast. One is sliding beneath the other. In a place for centuries, these plates have been locked together, accumulating stress. The question is not if they will slip, but when. Scientists monitor this locked fault with a network of seismometers, GPS stations, and pressure sensors, watching for any sign of movement. These ghost forests are not recent. They drowned in the year 1700, when the last great earthquake struck this coast. The trees drowned because the ground suddenly dropped several meters during that earthquake, allowing the sea to rush in and kill them. Pressure along the fault has been building for over 300 years. The last release was so violent that it sent a tsunami across the entire Pacific Ocean. Today, millions of people live along this coast, unaware that the ground beneath them is quietly storing energy for a megaquake that could strike at any moment. When it happens, the seafloor will lift by several meters, displacing billions of tons of water and launching a tsunami that will reach the coast in minutes. So the impossible question is not whether the Cascadia Megaquake will happen, but whether we will be ready when it does.
The Cascadia Subduction Zone stretches for over 1,000 kilometers beneath the Pacific, from northern California to southern British Columbia.
Here, the small Juan de Fuca plate, a fragment of ancient ocean floor, dives beneath the massive North American continent. As the plate sinks, it releases water into the hot mantle, causing rock to melt and feeding the long chain of Cascade volcanoes. Volcanoes like Mount St. Helens and Mount Rainier are direct products of this subduction, rising as snow-covered fire mountains. The plates are now locked, so the North American plate is being squeezed and pushed upward, storing elastic energy like a compressed spring. GPS stations dotting the coast measure the land's slow movement, revealing that the region is rising and shifting eastward every year.
Layers of sediment on the seafloor record underwater landslides triggered by past megaquakes, each layer a signature of ancient ground shaking.
The fault is locked under immense strain, with 3 centuries of accumulated stress now waiting to be released in a single rupture. Mapping shows the entire subduction zone can break at once, generating a magnitude 9 earthquake and a Pacific-wide tsunami. This is the hidden engine of the Pacific Northwest. A sleeping fault that builds the land, feeds the volcanoes. The seafloor near Cascadia holds layers of sand and mud that tumbled downhill in a single violent event long ago. In Japan, official records from the year 1700 describe a strange tsunami that arrived without any earthquake being felt locally. In the year 1700, the entire subduction zone likely ruptured at once, in a magnitude 9 earthquake that reshaped the coast. The tree rings of the ghost forest tell the same story. The trees died suddenly in the winter of 1700. The land did not just shake, it dropped. Forests were suddenly lowered into the sea, and freshwater marshes turned to salt. The waves crossed the entire Pacific Ocean, reaching Japan about 9 hours later, without warning and without any local earthquake. Japanese villagers recorded the strange wave as an orphan tsunami, a sea surge with no parent earthquake. That record became a key to the past. Indigenous oral histories from the Pacific Northwest also remember the ground shaking and the sea rising, preserving the event for generations without writing. In deep water, a tsunami is barely visible, moving at the speed of a jet, only becoming destructive when it reaches the shallows. The 1700 earthquake left its mark across the land and across the Pacific, a warning written in sand, trees, and old records. Beneath the water, the drowned roots of the ghost forest still stand, preserved for centuries by salt and mud. The bark is encrusted with barnacles, proof that these trees once stood in open salt water, not in the forest where they grew. From the air, the dead trunks stand in rows, a forest of gray pillars that once shaded a living coastal woodland. Each tide still rises and falls around the dead trees, the ocean returning again and again to the place it claimed 3 centuries ago. Salt crystals still form on the bark, drawn out by the drying seawater, a slow process that continues to etch the dead wood. At sunset, the ghost forest becomes a field of long shadows, each one a reminder of the living forest that vanished in a single night. Even now, life moves among the dead trunks, small creatures returning with each tide to the drowned ground where the forest once stood. Looking up through the bare branches, it is easy to forget that this was once a place of green leaves, birdsong, and fresh water.
In the still water, the dead trees are mirrored, creating a doubled image, as if the ghost forest reaches both upward and downward at once.
The ghost forest is not just a curiosity, it is a natural archive, preserving the exact moment when the land sank and the sea returned. On the night of January 26, 1700, the Pacific Ocean carried a secret eastward across the dark water toward Japan.
At dawn, the villages along the Japanese coast were beginning their day, unaware that an invisible wave was already crossing the ocean toward them.
In the official records of the time, Japanese scribes wrote of a strange wave that arrived without any felt earthquake, calling it an Orphan Tsunami. The wave took about 9 hours to cross the entire Pacific, moving at the speed of a jet in deep water.
In deep water, the tsunami was nearly invisible, a low swell only a few centimeters high, moving under the surface with enormous energy.
Some villages reported boats being lifted and overturned by the sudden surge, even though the sea had seemed calm only moments before. Today, the same coastline is lined with warning signs and seawalls, built in the shadow of a wave that arrived without warning 3 centuries ago.
Salt still clings to old wood along the coast, a reminder that the sea has reached places where it does not belong.
By tracing the wave backward from Japan, scientists calculated that it must have come from an earthquake off the coast of North America. The Orphan Tsunami had no local cause, but its story connected 2 distant shores and revealed a hidden fault beneath the Pacific Northwest. In March 21, this same type of subduction zone off Japan suddenly ruptured, producing one of the most powerful earthquakes ever recorded. The earthquake lifted a section of seafloor over 300 kilometers long, pushing the ocean upward and triggering a massive tsunami. Along the Tohoku coast, enormous seawalls now rise from the shore, built after 2011 to hold back the next great wave. Old tsunami stones still stand near the shore, carved with warnings. Do not build below this point, for the sea will return. In some harbors, the sea withdrew for minutes, leaving boats grounded, before returning as a wall of dark water. Entire coastal forests were flattened by the wave, their trunks snapped and turned inland, a record of the water's force. Tide gauges along the coast recorded the arrival of the tsunami as a sudden, violent spike in sea level. The 2011 Japan event is the closest modern parallel to what scientists expect from Cascadia. After 21, Japan built hundreds of tsunami evacuation towers, giving people a place to climb above the waves. The 2011 disaster showed what a subduction megaquake can do, and the memory now drives preparations across the entire Pacific. Deep on the seafloor, unmanned seismometers listen to the quiet sounds of the fault, recording tremors too small to feel. Sometimes the fault does not rupture. It creeps slowly in events called slow slip, releasing stress quietly over weeks. Methane seeps and gas vents dot the Cascadia margin, marking where deep tectonic pressure forces fluids up through the seafloor. Raised coastal terraces reveal that this coast has been lifted during ancient earthquakes, each step marking a different era of sudden motion. Along the coast, hot springs and mud pools hint at the deep heat and pressure beneath, driven by the same forces that power the subduction zone. Below the locked fault, deep tremors occur almost constantly, a kind of slow seismic noise that scientists call episodic tremor and slip.
Satellite radar measures the land's surface moving by millimeters, revealing patterns of strain that are invisible to the naked eye.
Below the locked zone, the fault behaves unpredictably, generating deep tremors and slow slip that may help trigger or delay the next great earthquake. Even in the deep ocean, the subduction zone reveals itself through vents and seeps, releasing heat and chemicals from the Earth's interior. The fault does not follow a simple schedule. It rumbles, creeps, and sometimes goes silent. Far out at sea, a network of tsunami buoys floats above the Cascadia Subduction Zone, watching for the first sign of a passing wave. On the ocean floor, pressure sensors measure the weight of the water column, detecting the passing tsunami wave long before it reaches shore. Even the fiber optic cables that carry internet traffic across the ocean floor can sense the pressure and vibration of an approaching tsunami.
Coastal tide gauges record the slow rise of the sea, and would capture the first abnormal wave surge as the tsunami enters shallow water.
GPS stations on the coast measure the slow, silent strain building in the earth, showing that the land is being squeezed like a spring.
From space, radar satellites map the bending of the Earth's surface, revealing where strain is accumulating along the locked fault.
Fresh cracks along coastal bluffs are another warning sign, showing that the land is slowly bending under the strain of the locked fault.
Thousands of tiny earthquakes occur along the fault each year, most too small to feel. But they reveal where the plates are locked and where they are moving.
Along the coast, tsunami sirens stand ready, built to warn communities within seconds of a confirmed offshore earthquake.
These warning systems are our first line of defense, but they can only give minutes of notice before the great wave arrives.
In laboratories, East Asian scientists recreate tsunamis in miniature, using long wave tanks to study how these waves form, travel, and break. A tsunami wave in the deep ocean is not a towering wall, but a long, low swell that can pass unnoticed, just as it did in 1700. Computer simulations show how the wave begins as a broad uplift of the seafloor, then steepens into a powerful surge near shore.
Waves bend and focus around headlands and bays, meaning some beaches receive a much larger surge than others, even from the same tsunami.
Engineers use detailed models to predict which neighborhoods will flood first and how deep the water will reach. Simulations show that within minutes, the wave could flood low-lying areas, turning streets into rivers and sweeping away structures.
Along steep bluffs, waves can run up to heights far above sea level, then drag everything back into the ocean.
Even a small-scale model shows how bridges and roads can be torn apart by the sheer force of a tsunami wave. Flood zone maps show the areas most at risk, helping authorities plan evacuation routes and prepare coastal communities for the worst.
These simulations are not predictions of a specific date, but they show what will happen when the locked fault finally...
Along the Pacific Northwest coast, a new kind of structure has begun to rise, the Tsunami Evacuation Tower, built for the day the ground begins to shake. These towers are built to withstand the shaking of a great earthquake and to hold survivors above the reach of the incoming wave. The handrails are already weathering under the salt air, a reminder that these towers must survive in one of the harshest coastal environments on Earth.
In some towns, the towers are placed within walking distance of homes and schools, designed so that residents can reach them in minutes.
Engineers design the towers to remain standing even if the ground shifts, the wave surges, and debris strikes the lower columns.
Evacuation route signs mark the path to safety, pointing toward high ground and towers that can be reached on foot.
In flatter areas, artificial hills and berms provide an alternative to towers, giving people high ground where none existed before. The stairs are built wide and textured so that many people can climb quickly and safely, even in rain or darkness. Simulations show that even in a worst-case tsunami, the upper platform of these towers remains above the highest wave, offering a dry and stable refuge. These towers are more than concrete and steel. They are a promise that when the earth moves and the ocean rises, there will be a path to safety. Along the Cascadia coast, a dense array of seismic stations listens around the clock for the first faint tremors of a great earthquake. Seismologists watch these traces for patterns that might warn of an impending rupture, but the Earth rarely gives clear signals. Scientists cannot predict the exact date, but they estimate a significant probability of a major Cascadia earthquake within the next 50 years. Every day, these stations measure the slow, relentless motion of the land, building a picture of how much strain the fault has stored. Satellite radar can detect movements of just a few millimeters per year, revealing where the fault is locked and where it is creeping. Even the global network of undersea fiber optic cables can now sense the tiny vibrations of the Earth, turning communication lines into seismic sensors.
When an earthquake is detected offshore, these sirens can give coastal communities a few critical minutes to reach higher ground before the wave arrives.
Computer models can simulate many possible rupture scenarios, but no two earthquakes are identical, and the next one could unfold in an unexpected way. Past records of tsunamis and their arrival times help scientists calibrate models, but each event leaves its own unique signature.
The science of prediction is not about knowing the day or the hour. It is about understanding the risk.
The first blow is the earthquake itself. Violent shaking that can last for minutes, toppling buildings and cracking the ground. In waterlogged soils, the shaking turns solid ground into liquid, causing sand and water to erupt from cracks.
The second blow follows within minutes. A tsunami generated by the same fault, striking while the ground is still shaking. Earthquake-triggered landslides send cliffs and hillsides tumbling into the sea, adding to the chaos.
Broken gas lines and downed power lines ignite fires, turning damaged neighborhoods into additional danger zones.
Aftershocks continue for weeks, further weakening already damaged buildings and slowing the recovery of the coast.
When the tsunami arrives, it finds a landscape already shattered, sweeping away what the earthquake left standing. In time-lapse, the double disaster unfolds with terrible speed, shaking, then the sea retreating, then the wave returning. After the shaking and the wave, the coast is left silent, its shape changed forever by the double blow.
The double whammy is why Cascadia is so dangerous. It is not one disaster, but two, arriving together.
The human cost begins with infrastructure. Bridges that collapse, cutting off communities from aid and escape when they need it most.
Water mains rupture, flooding streets and cutting off clean water, while broken sewer lines threaten disease in the aftermath.
Schools are among the most vulnerable places, empty halls and fallen debris, where the daily life of a community is suddenly interrupted.
Ports and harbors are destroyed, severing supply lines and leaving communities isolated from food, fuel, and medical supplies. Power grids fail, plunging entire regions into darkness, disrupting hospitals, water systems, and communication for weeks or months.
Coastal roads are carved away, leaving communities cut off by land and by sea, unreachable by rescue teams.
Hospitals themselves are damaged, forcing the injured to be treated in the open or in temporary shelters without power or water.
Rail lines are twisted beyond use, halting the transport of goods and people across the region. The smaller losses are the hardest to measure. Playgrounds abandoned, homes emptied, and the quiet spaces where daily life once happened. The human cost is not only in the moment of shaking or the wave, but in the months and years of recovery that follow. Deep beneath the sea, the fault holds its secrets, the locked sections still silent, while below, the earth creeps and trembles.
The most haunting mystery is not if the earthquake will come, but when, and whether it will break the entire fault at once.
From space, the fault is mapped, yet the exact pattern of the next rupture remains hidden, a shifting shadow of uncertainty. The ghost forest remembers the last great earthquake, but it cannot tell us when the next one will come. Only that it will. Will it be a full margin rupture, unleashing a magnitude 9, or a smaller segment breaking? The Earth has not told us. The Orphan Tsunami record is a clue, but it leaves gaps, like a torn page in a history book we are still trying to read. New cracks and seeps appear along the margin, but whether they signal an impending rupture or just the Earth's slow breathing, we cannot yet say. The landscape above changes with the seasons, but below, the fault waits, patient and silent, adding to the mystery.
Gravity maps reveal the deep structure, but the fine details of the locked zone remain blurred, a mystery that only time will resolve.
And so the greatest remaining mystery is the timing, hidden somewhere in the dark water and silent earth, waiting to be revealed. We began with a question. When will the great earthquake strike this coast, and what will it leave behind? The land recovers, and life returns to the cliffs and forests, just as it has after every great earthquake in the past. The sea that once drowned the ghost forest still touches this coast every day, a quiet reminder that the boundary between land and water is never permanent.
The lighthouses and warning sirens along this coast are not only for ships, they are symbols of our effort to prepare for what the Earth might do.
The fault does not follow our clocks or calendars. It operates on its own timescale, measured in centuries, and we are only beginning to understand it.
Above the fault, the ocean is full of life, and the coastal forests are green and thriving. The danger is hidden, but the beauty is real.
Fiend from space. The Cascadia Fault is just a line, but for those who live along it, that line. These forests have stood through many earthquakes, and they will stand again after the next one. The land remembers how to recover. The greatest remaining mystery is not whether the Earth will move, but when and how ready we will be. The file is closed. The mystery remains.